Today, we're going to talk about acids and bases. So acids and bases are a specific type of equilibrium. So if you're ever confused, just remember that these still follow the same mathematical rules and principles as other equilibrium reactions, okay? So what is an acid or a base? For now, we're going to use the Bronsted-Lowry model or definition of acids and bases. So under this definition, we can say that an acid is a source of H plus and bases accept H plus, okay? So this is the Bronsted-Lowry model of acids and bases. So for example, here we have hydrochloric acid, HCl, and it goes to H plus and Cl minus. So you're forming H plus. So this is a Bronsted-Lowry acid. And here, ammonia, NH3, is accepting H plus to form ammonium. So it's a Bronsted-Lowry base. So how many of you have heard the term pH before? Yeah. So pH is defined as like the negative logarithm of the concentration of hydrogen, H plus, but POH is a little bit more obscure, and this is the negative log of the concentration of OH minus. Okay. So this is the common log, so log base 10, and that means that if you have one change of unit in a change of one pH unit, you will have a tenfold change in the concentration of H plus. So minor changes in pH actually can mean quite a big thing when you're talking about like the concentration of H plus. So here we can see like the different pH values. So 7 is a neutral pH. So the 7 is the pH of pure water at room temperature. And in this direction, we're getting fairly acidic. So we have vinegar, lemon juice, and car battery acid. So your car battery uses sulfuric acid. And I believe the reaction is sulfuric acid plus lead oxide goes to lead sulfate. So you have these sheets of lead hanging in a bath of sulfuric acid, and these lead sheets are covered in a layer of like lead oxide and lead sulfate, and the reaction forms lead sulfate, and this creates a voltage, which we'll talk more about in electrochemistry. So so you can say so pure water has a hydrogen ion concentration of 10 to the minus 7, right? And car battery acid has a concentration of 10 to the minus 0, so 1 molar. So this is all in moles per liter. So that means car battery acid is like 10 million times more acidic than water, right? And vinegar is 10,000 times more acidic than water. And a drain cleaner is maybe 10 million times more basic than water. So in this direction, things become more acidic. Here we have things that are more basic. And another term you'll hear for basic things is alkaline. Okay. So so drain cleaner is sodium hydroxide, by the way. So you have these OH minus ions that will react with water to form these OH minus ions react with acids to form water. So very strong base. Okay. So interestingly enough, a lot of acids can be quite sharp or like tangy. So like lemon juice and vinegar. while a lot of bases are more bitter. So yeah, but don't taste any of these things. That's not a good idea. Okay. Um, so I did want to talk a little bit about ocean acidification because it relates to the idea of acids and bases. So there's a magazine published by the American Chemical Society called Chem Matters. So I'll write that down. So there's a magazine published by the American Chemical Society, the ACS, called Chem Matters. So here I have an article from 2018, and it's about ocean acidification. So we know to produce the energy that you use in your house, about 40% of that energy comes from coal, I think. So the vast majority of the energy that we use in our homes in our day-to-day lives is either made from coal or natural gas. And the major combustion byproduct of this process is carbon dioxide. And at first, carbon dioxide doesn't really look like an acid. It doesn't have any hydrogen ions, hydrogens it can donate, which remember is the definition of an acid under the Bronsted-Lowry definition. But carbon dioxide does react with water to form carbonic acid, so H2CO3. And here you can see we have the hydrogen atoms that get donated. And so this has caused a decrease in the pH of the ocean. So in the past few years, we've gone from like 8.2 to more 8.1. So although this doesn't look like a big change, if you remember it's a logarithm scale. So this is actually, let me see. We can calculate this, 10 to the minus 8.2 and then 10 to the minus 8.1. So it's about a 26% change. So it's actually quite significant. So we're seeing a significant decrease in the pH of the ocean. It's becoming more acidic. And the problem with this is that, a lot of marine life, so your corals and shellfish, they have shells and skeletons that are made of calcium carbonate. And so see, we can have carbonate ions. And these carbonate ions react with carbonic acid to form bicarbonate. And bicarbonate is very soluble in water. So this means that over time, shellfish and corals are going to start dissolving. So if you want to see this experiment yourself, what you can do is go to the beach, pick up a couple of seashells, and leave them in vinegar overnight. And if you measure the mass before the vinegar and measure the mass after the vinegar, you'll see a significant mass change. So a lot of the shell will be actually dissolved. Yeah. So, and you can see that over time, we see a very large increase in the concentration of CO2. So CO2 concentration is given in parts per million of volume. And so the pressure of CO2 in microatmospheres, you can see, is also increasing. The partial pressure of CO2 in seawater. So yeah. So you can see how there's a very strong correlation between the decreasing pH and the increasing CO2 from greenhouse gases. So this is very important because this has a very negative impacts on coral reefs because coral reefs, again, are made of calcium carbonate, which will dissolve. So if all the coral reefs kind of die, then the fish that are associated with those coral reefs will also die. And a huge portion of the world's biodiversity is located within coral reefs. So this will have major impacts on the fishing industry and etc. So just to show how acids and bases are important in our daily lives. Okay. So Okay, so you can dissolve acids and bases in any solvent you want, and they will have different properties. Acidity and basicity are really are heavily dependent on solvent properties. But for now, we will mainly talk about stuff dissolved in water because you're made of water. The oceans are filled with water, um, and in a high school setting, everything will just you'll see acids and bases mainly in water. So water is a very common solvent. Um, so one very important reaction that water undergoes is this reaction, autoprotolysis. So two water molecules react to form one H3O plus molecule. So this is called the hydronium ion plus one OH minus. So a hydroxide ion. So let me write that. Hydronium and hydroxide. So we have the hydronium ion and the hydroxide ion. And this reaction has an equilibrium constant of 10 to the minus 14. So we have Kw equals 10 to the minus 14. And this is at room temperature. So you may have heard a lot of people say that pure water is electrically non-conductive. But it turns out that you will always have a very, very small concentration of these hydronium ions and these hydroxide ions, which will give rise to some very small conductivity. So how do we interpret this Kw? Well, the equilibrium constant is equal to OH minus, the concentration of OH minus, times the concentration of hydronium. And this equals Kw. Okay? And the major takeaway from this is that we have pH plus POH equals 14. So pH plus POH is 14. So you should write that down. So that means if the pH increases, the POH has to decrease. And this makes sense, right? Because if you have a high concentration of H plus, you have to have a low concentration of OH minus and vice versa. So let's have some examples of acid-base reactions. So here you can see HCl and then H2O forms hydronium plus Cl minus. So the HCl is losing this hydrogen atom, this proton. So a lot of times you'll hear H plus referred to as a proton. So it loses a proton to form Cl minus. Meanwhile, our base, which is water, accepts a proton to form H3O plus. Likewise, we have NH3, which is a base. So it accepts a proton to form NH4 plus. And the opposite for HF. So HF is an acid, it loses a proton to form the fluoride ion. And you can see the same for here. So water can act as an acid or a base. So in both situations, they have it acting as a base. But water can also donate H plus. So you saw here, so you saw like water can either accept a proton or it can donate a proton. So water is acidic and basic at the same time, which is called a property called amphoterism. And here, one more example. So the fluoride ion forms HF, and then the dihydrogen phosphate ion loses a proton to form a monohydrogen phosphate. So here's a problem. So I'll just let you think about it for a minute. So write the reaction between hydrochloric acid and sodium hydroxide. Identify the acid and the base, and write the reverse reaction and identify the acid and base in that situation. Okay. So what do we have? That's kind of interesting. So let me try to get. Okay. Where's my pen? 1 second. So what do we have? We have HCl and NaOH. And what might be helpful is to realize that we can split this up into two ions, Na plus and OH minus. So does anyone have a guess as to which one of these components is the acid and the base? So which one of these is acid or base? So remember, acids donate H plus. Great, right. So if OH were to lose a proton, we form this O2 minus ion, and it's very difficult to actually form this O2 minus ion in aqueous solution when it's dissolved in water, because this will immediately, any oxide ion will immediately react with water to form hydroxide. Also, so we have this very large charge on a relatively small atom, so it's a bit difficult. On the other hand, this is a very favorable reaction. K equals like 10 to the fifth power or something like that. So yeah, so because we form this very stable chloride ion. So chloride is very stable. So the reaction is plus HCl plus. So Cl minus loses a proton, so it forms Cl minus. The OH minus gains a proton, so we form water plus plus. And notice this, we have this reaction. So just as a tie-in to the last lecture, we have basically the reaction H plus plus OH minus goes to H2O. Now, what do you think the K of this reaction equals? The equilibrium constant. So you might want to look back to your notes. The reaction of H2O goes to H plus OH minus has Kw equals 10 to the minus 14. So this is the reverse of that. So this should have 1 over Kw equals 10 to the 14th. So we can calculate delta G, and if I remember correctly, it's about negative 50 kilojoules. So delta G is approximately negative 50 kilojoules. And this, of course, corresponds to a huge release of energy. So we release a huge amount of energy. So it turns out that this reaction is very highly exothermic, and so it releases a lot of heat. So I remember adding like hydrochloric acid to sodium hydroxide pellets, and there's a very vigorous reaction. It gets very, very hot. Okay, so onto this. So we have acid here and base here. What about the reverse reaction? And we can leave out Na plus because it doesn't do anything. Cl minus plus H2O goes to HCl. Right. Now, can someone identify the base and the acid and the base in this reaction? So acids accept proton. Acids donate protons, and bases accept them. So which one is accepting the proton, and which one's donating the proton? So you can see that Cl minus is accepting an H plus to form HCl, right? So this is the base. And here we have H2O is donating a proton to form OH minus. So this is the acid. Okay. Does that make sense? Should we do one more example? So, like, for example, let's say we have so which one is the acid and which one's the base here? Right. So which one is donating a proton? So this one donates a proton to form HCO3 minus. This one accepts a proton. Oh, there should be a 2 there. So this is the acid, and this is the base. Okay. So the reason why I had you consider the reverse reaction is because I want to introduce the idea of conjugate acid-base pairs. So take a look at this reaction, these two reactions. So what I want you to notice is that one of the reactions is simply the reverse of the other. So I just flip the reaction around. And what I want you to notice is that we can create these pairs. Right. We've created pairs of acids and bases. Here, since here H3O plus acts as an acid and H2O acts as a base, right? And HA acts as an acid, A minus acts as a base. So we have these pairs of acids and bases. So HA is an acid, A minus is a base. So we call these conjugate acids and bases. So A minus is the conjugate base of HA. And HA is the conjugate acid of A minus. So, of course, you can see that HA donates H plus, forming H minus. So we consider it to be the acid, and A minus accepts the H plus to form HA and is considered to be the base. So based on this knowledge, which one of these do you think is the conjugate acid and the conjugate base? Anyone? So which one of these is the acid and which one of these is the conjugate base? Right. H3O plus is an acid because it will donate an H plus to form H2O. But H2O is the base since it will accept H plus to form H3O plus. So, um, ah, yeah. So I have a problem. So maybe 10 minutes, 5 minutes, something like that. So just do these problems, these two problems, and then I'll come back in a minute. Now, can someone tell me whether HF is an acid or a base? Do you think HF is an acid or a base? Right. HF is an acid. It's hydrofluoric acid. Because if it were to act as a base, then we would form H2F plus. And now we have this positive charge on like a fluorine atom, and it's not super good. Okay. So no. So HF is a base acid. Right. So can someone label these with acid, base, conjugate acid, and conjugate base? Right. Can someone label these? Can someone label these things? So 1, 2. So let's start off with the acid. What's the acid in this case? Right. HF. And acids need to react with bases. So what's acting as the base? Great. Water. And now we can create our pairs. So what's the conjugate acid? So is this an acid? Is that an acid? Great. So can you tell me why it's not an acid? Great. Right. Exactly. So this one receives protons. It doesn't donate protons. It doesn't have protons to donate. So this is the conjugate base. So our conjugate base is F minus. And of course, this is also not, this is not a base. This is an acid. So our conjugate acid is H3O plus. So does that clarify what conjugate acids and conjugate bases are? Okay. So let's do the rest of the problems. It's a base or an acid, and then you can do the So identify whether these are bases or acids, and then write the formulas of their conjugate acids or bases. So first, so let's look at this one. Is this a base or an acid? Great, base. So we can react with water, just any, to form OH minus plus. What do we form? So remember, so make sure to balance your reaction. So this oxygen goes to here, right? So we need to keep this all the same. And then we need to add an H plus. So what's the overall charge here? So this should be 1 minus, right? Because we're combining 2 minus with 1 H plus. So 2 minus 1 is 1. So we have 1 minus. And this is the conjugate acid, right? Because this acts as an acid to form CO3 minus. So, like, can someone tell me what the conjugate base of this acid is? What's the conjugate base? So the conjugate base should be able to accept a proton to form the acid. So what species will accept a proton to form HNO3? So it should be NO3 minus, right? Because NO3 minus is a base that will react with H plus to form HNO3. Okay. And finally, we have NaOH, and NaOH is a base, and its conjugate acid is H2O. So the final question is just something to think about. So is the role of a conjugate acid in the reverse direction the same as the role of the acid in the forward direction? So the role of the acid in the forward direction is to donate H plus. The conjugate acid in the reverse reaction also donates H plus. So they fill the same role, right? Yeah. The role, yeah. Okay. How do I clear everything? Here, clear up. Okay. So, let's talk about strong acids and weak acids, and strong bases and weak bases. So this definition is actually fairly simple. Let's say we have this generic reaction, some acid plus water goes to A minus plus H3O plus. If the reaction goes to completion, the acid is strong. That's it. If the reaction does not go to completion, then the acid is considered to be weak. So some examples of strong acids, you should write this down, are the most common ones at least, are HCl, HNO3, H2SO4. So these will go to completion. So actually I'll hold off on that for a second. So these are the three major strong acids, the major strong mineral acids that you'll see. So what are their uses? So HCl is often used in pools and is just a very common industrial chemical, and it's often produced as a byproduct. And HNO3 is a very strong oxidizing agent. Most acids will not react with copper or silver or stuff like that. Well, HNO3 will react with them. And H2SO4 is actually the most commonly produced chemical in the world, used in car batteries and just general acid, just stuff. If you need an acid, you use H2SO4. And interestingly, a mixture of HCl and HNO3 is called aqua regia, royal water. And it's called royal water because this is one of the very few mixtures that can dissolve gold and platinum. So gold and platinum are very unreactive metals, which makes them desirable for jewelry. since they won't corrode and dull over time. But they are dissolved by aqua regia. And the way this works is like, so the HNO3 will dissolve a very, very small portion of the gold, not enough to be noticeable. But then this very small amount of dissolved gold reacts with HCl to form a gold chloride complex. So this complex. So the formation of this complex is what makes the reaction favorable. So this is very interesting because so this is hydrochloric acid, nitric acid, and sulfuric acid. And hydrochloric acid cannot dissolve gold. Nitric acid cannot dissolve gold, but together, combined, they can. Okay, so that's just a minor side note. So, and of course, the same thing goes for bases. So we have some base plus water goes to the conjugate acid of the base plus hydroxide. And of course, if this reaction goes to completion, it's strong. If it doesn't, it's weak. So common strong. Also, strong bases include salts of hydroxide salts. So NaOH, calcium hydroxide, or slaked lime. So salts that contain OH minus are often strong. Weak bases include ammonia, sodium carbonate, stuff like that. And in organic chemistry, there are a lot of what we call super bases. So these are very, very, very strong bases. Bases so strong that they don't exist in aqueous solution because they just react with water. So for example, your organolithiums, compounds of carbon and lithium. So very strong bases. So I'll do the first problem. So calculate the pH of a 0.2 molar HCl solution. HCl is, of course, a strong acid. So the reaction is HCl goes to H plus Cl minus. And I didn't include the water molecule because it's just easier for me to write this way. So this reaction goes to completion. So all of the HCl gets converted to H plus. All of it gets converted to H plus. With this information, what do you think the concentration of H plus is? So all of the HCl is converted to H plus. So then the concentration of H plus should also be 0.2 molar, right? And then remember, we have pH equals negative log H plus. So pH equals the negative log of 0.2, which is so we have a pH of 0.70. So I'll let you do the second problem. So remember, calcium hydroxide will, oh, this is not realistic. Change that to barium, Ba. Change that to barium. So we have a 0.4 molar barium hydroxide solution. It doesn't change anything, but whatever, just to make it more realistic. So this is a strong base, so it will disassociate completely. And you can calculate the pOH first, and then you calculate pH. So I'll give you 5 minutes, and I'll just wait until someone has an answer. 0.398 is not quite correct, but it's close. So the reaction we need to consider is Ba right? So we have this salt, barium hydroxide, and it completely dissociates into barium 2 plus and 2OH minus. Okay, so the concentration of this is 0.4 molar. But notice that one of these produces 2 moles of that. So the concentration of this should be 0.8 molar. Hence, and this equals 0.01. Right? Let me check. Yeah, 0.01. 0.096 to be exact. And then furthermore, we have POH equals 14 minus pH, right? Since pH plus POH equals 14, which you should know. This equation you should know. So therefore, we have pH equals 13.9. And this is a very basic solution. So this is a very strongly basic alkaline solution. So let's take a 10-minute break, okay? So come back at 8 o'clock or about now. Okay, good. So now we're ready to talk about weak acids and bases. And unfortunately, these are a little bit more complicated than strong acids and bases, but they're not too bad. Just treat them as normal equilibrium, okay? It's a normal equilibrium problem. So we have this reaction, generic weak acid plus H2O goes to A minus plus H2O plus. And the quintessential weak acid would probably be acetic acid. So it's in vinegar. So acetic acid and vinegar. Other common acids are citric acid, like nitrous acid, bisulfate is a weak acid. Yeah, so that kind of thing. Phosphoric acid. Yeah. So these do not go to completion. So that means we're going to have a mixture of A minus, H3O plus, and HA. So we have some mixture of A minus and HA. In other words, we have a mixture of the acid and its conjugate base, right? We have a mixture of the acid HA and the conjugate base A minus. So the reaction doesn't go to completion, and we establish an equilibrium where we have Ka, which is known as the acid dissociation constant. So you can just call it the acidity constant if you want. And with Ka, of course, equals concentration of H plus times the concentration of A minus divided by the concentration of HA. And the important thing here to realize is that for most cases, the concentration of H plus is approximately equal to the concentration of A minus. Right? Because the only other acid present is water when we're considering these kinds of problems, and water is such a weak acid that we can neglect it. So we can assume that H3O plus is equal to the concentration of A minus. And then after that, we have a very simple quadratic equation. Furthermore, we can assume that the concentration of HA does not change. So we're usually given the concentration of the acid, and this and since the equilibrium constant is usually very, very small, 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, we assume that HA does not change. So we simply plug in 0.5 molar into HA. So I'll let you solve this one, give you a minute to do that. It might be helpful to construct an ICE diagram, ICE diagram, but here it's so simple, I don't think that's really necessary. We're only really considering a few things. So what was the acid? We have, okay, it's HF, right? Hydrofluoric acid. Hydrofluoric acid is interesting because although it's a weak acid, it's much more dangerous than the other acids I've talked about, since HF will attack your skin and bones and you won't feel it until maybe several hours later. And by then your bones are already dissolving. So very nasty stuff. basically, if I remember correctly, it will HF will bind to the calcium in your bones. So it penetrates the skin very quickly, and you don't feel it. So you don't know that you don't know that your bones and your skin are getting attacked until like maybe 12 hours, 6 hours later, and then by then the flesh is already dying. So HF is very, very dangerous. So it's definitely it's one of the really dangerous chemicals. Something I wouldn't want to work with. Yeah. So the other like strong acids like sulfuric acid, nitric acid, hydrochloric acid, much, much safer than HF, even though they're much stronger. Okay. So H2O goes to H3O plus. Right. So the first thing I want you to notice is that is approximately to F minus, right? Does everyone see why this is the case? Does everyone understand this statement? So the only reaction, you can see that 1 mole of this will produce 1 mole of that and 1 mole of that. So we're producing these in equal amounts, hence they're equal. So we can say this is X. Furthermore, we can say that HF does not change because K is very small. These two statements give us this equation, X squared over and then this equals to 0.045, and then negative log of 0.045 equals 1.35. So this is the pH. And I want you to notice that if we consider the pH of a similar strong acid, so let's say we have 0.5 molar strong acid, and the pH equals calculator doesn't want to cooperate. And then the pH equals 0.3. So you can see there's quite a big difference in the pH between a strong and a weak acid. Okay. The mathematics is basically the same thing for weak bases. So you might see, so we have some generic weak base plus H2O goes to BH plus OH minus. So we have Kb equals OH minus times BH plus divided by BH minus. So just go ahead and do this one, I guess. Maybe I'll give you a minute to do that. The main question is like, do you understand how to solve the problem? So I guess like what I'm trying to, because like I haven't seen anyone post solutions to these kinds of mathematical problems. So I don't know if it's because you don't know how to solve the problem or because you need more time. So do you want more time or do you want me to explain this problem? Okay, I can do that. We're given 0.3 molar and Kb equals 10 to the minus 4.75. Great. Okay. Okay, there we go. So NH3 plus H2O. Does anyone know what the products are? So remember, this is a base, and this is an acid. So what should the products be? So ammonia is a very, very weak acid. So that reaction does not actually happen. This doesn't really act as an acid under normal conditions. But I guess if you study some organic chemistry, you might see like something like sodium amide. But so this is a base and this is an acid. So what do you think the product should be? Yeah, NH2 minus is pretty unstable. So we don't form that in aqueous solution. So the base accepts a proton. So what do we get when this accepts a proton? What do we get when this base accepts a proton? Great. And what else do we get? Great. Perfect. Now, do you think these two things are equal to each other? Is this and this equal? Are these equal? Great. This concentration is equal to this concentration. Additionally, do you agree? You can see that this is a rather small number, right? I think that's a 2. Yeah, that's a small number, right? So we can assume that this doesn't change. So what should our expression be? What equation should we solve? Oh, so we have that. Right? But when we consider this, we get OH minus squared divided by NH3 equals 10 to the minus 4.25. And then what does NH3 equal? What does this equal? Great, 0.3 molar. Can someone solve the equation for OH minus? What does that equal? Oh, is that the POH? Let me check that. I'm not sure where that number comes from. Oh, do you mean? Oh, so 1.687 to the minus 5 is the concentration, is OH minus squared. So you need to take the square root of that. You need to take the square root of that and then take the log for them. But I think that this equation is self-explanatory. So just solve for OH minus and then take the log of it, take the negative log of that to get the POH. So you take the negative log of hydroxide concentration to get the POH, and then simply take that, and then you use POH plus pH equals 14 to find the pH. Okay. Now, there's one other topic I wanted to talk about. So, titration. You may have, has anyone heard of the term titration before? Nope. Well, titration is very important in analytical chemistry. Titration is a technique to determine concentrations of unknown solutions. So let's say you like have some sample, like I don't know, maybe a food sample, and you want to test like how much stuff is in that food sample. Well, you could perform a titration. So as a matter of fact, at chemistry camp, the chemistry Olympiad camp, I did a titration of aspirin. So you react aspirin with concentrated sodium with sodium hydroxide, and then you back titrate that, which I won't explain right now. You back titrate the extra hydroxide with HCl, and then from that you can actually pretty accurate. You can determine the concentration of aspirin in your tablet. Okay, so let's just suppose we have an unknown amount of acid and base, or base, acid or base. Then you can titrate it. So you react with some amount of base or acid. So if you have an unknown acid, you react with base. If you have an unknown base, you react with acid. Here we have unknown acid, so we react with base. And the base has a known concentration. We know how concentrated this base is, and we can measure the volume using a burette. Using this burette, we can easily measure the volume. That means we can calculate the total number of moles of base. From that, because we know the total number of moles of base, we can determine the moles of acid. And we know the volume of this acid, so we can determine the concentration. Okay? So, and we usually add an indicator. I don't have an indicator with me right now, but a fun little thing to do is take some red cabbage. So red cabbage, go to the grocery store, buy some red cabbage, chop it up into little pieces, boil for 10 minutes, and then now you have this purple liquid, red cabbage juice, and this red cabbage juice will actually change color based on pH. So the dyes in the red cabbage have different forms depending on the pH, and this results in a color change depending on pH. And this is the principle behind indicators. So the indicator is itself an acid or a base, and it will change form based depending on the pH, and a different form results in a different color. So I think what's depicted here is phenolphthalein. So phenolphthalein is colorless in acid and a very nice pink in base. And you can see, and the phenolphthalein endpoint, so when the two things are equal, when the amount of acid and base is equal, the color you have a very rapid color change at what's called the equivalence point. And here, this is a little bit past the equivalence point. The ideal color is a very, very pale pink. This is kind of more of a dark pink, so it's not good technique. So yeah, so whoever did this drawing did not have good technique. But yeah. So let's just do this example. We have 25 mils of H2SO4, and we titrate it, and this titration requires 34.56 mils of 1 molar NaOH. What is the acid concentration? Well, before you do anything, you need to write down the reaction between the base and the acid. It's very important. So we can do that. So H2SO4 has 2 protons. It's diprotic. 2 protons. So it reacts with 2 moles of NaOH. Okay? Oh, H2O. H2O. That should be H2O. Okay. So now we have this. And now, does everyone see? So the moles of NaOH equals 1/2, is twice the moles of H2SO4. Does everyone agree with this statement? Because you can see that 1 mole of sulfuric acid reacts with 2 moles of NaOH. Hence, the moles of NaOH should be twice the moles of H2SO4. And N stands for number of moles. Okay? So, what do we do? So we need to find we need to find this value first. And remember that concentration equals N over V. So N equals C times V. And the concentration is given. The concentration is 0.1 molar. And the volume is also given. The volume is 0.03456 liters. So we can find N equals 0.003456 mole. This is how much NaOH we have, but we want to find how much H2SO4 we have. So we simply divide this by 2 to get to get 0.001728 moles. And remember, we want the concentration, so we do N over V equals 0.01728 divided by 25 milliliters. And then that gives us 0.069 molar. Remember, we have to convert milliliters to liters. So 25 milliliters equals 0.025 liters. So this is the idea behind titration. So you find the number of moles that you've added, and this is the number of moles in the unknown solution. And then from the number of moles in the unknown solution, it's very easy to calculate the concentration. Yeah. So does this make sense? Does this all kind of make sense? Okay. So has everyone written everything down? Okay. Let's see how much time we have left. Half an hour. Okay. So I just want you to look at this. So we have a titration curve. So this is actually very similar to the thing that we just looked at, except the numbers are different, but that doesn't matter. So we have some acid. So we have a very low pH because it's an acid, and we react it with base. So by reacting it with base, the pH will increase. And you can see at first, we have a very slow increase in pH. So the pH will change very, very slowly. But then at the equivalence point, we have this very rapid change in pH. Very rapid change in pH. And this rapid change in pH is what causes the very quick change in color. And this is why titration is so accurate, because the change is so fast. So you can really precisely pinpoint in this area. And then here we have a diprotic acid. So this acid will react with 2 equivalents of alkali, of base. So this is why we have 2 of these lines, 2 of these equivalence points. And then the pH will continue to change. And then we have the second equivalence point, very, very sharp change in pH, followed by, and now here, the reaction is complete, and we're just adding extra hydroxide, which increases the pH more and more, albeit very slowly. So yeah, this is titration curves. And I do want to talk about one other topic. So 2 more topics. So the first one is Lewis acids and bases, and you don't really need to worry about this too much. I just want you to know that Lewis acids accept electron pairs, so lone pairs, and Lewis bases donate lone pairs. So the most common example of a Lewis base would be ammonia, and a very common example of a Lewis acid is BH3, boring. So to illustrate how this works, we'll use this system, NH3BH3. So, you know, BH3 is sp2 hybridized. So we have B and this empty p orbital. We have an empty p orbital. And this empty p orbital can accept electrons. It's from NH3. So these electrons will go into the p orbital, and then you get something that looks like this. And why is this? Okay, another example would be CO2. So this carbon has a partial positive charge, and because these oxygens are pulling electrons away from the carbon. So this carbon will actually also accept electrons from something else, like water. So carbon dioxide is a Lewis base. Lewis acid. And there's one very, very interesting application of this. So let me draw you the structure of a Lewis acid. By the way, these vertices, I didn't draw the letter, but they're carbon atoms. And we have a bunch of fluorines here. So this is a very strong Lewis acid. We have an empty p orbital, and we have these fluorines pulling electrons away from the boron atom. So very strong Lewis acid. And then we also have triphenylphosphine, I believe. This could be, I can't remember it exactly, but I think it's triphenylphosphine. All you need to know is the phenyl groups are very big. They're like kind of like this. They're rather large. So this is the phenyl group. So basically, normally this and this would just react, but they have very large things on the side. And these things block each other in a sort of way, so they actually can't react. And we call this a frustrated Lewis acid-base pair. And and the application of this is that we can split up this hydrogen molecule. So the electrons from the hydrogen molecule go to the boron, and then this phosphorus donates that to the hydrogen, donates electrons to the hydrogen. So we end up getting something that looks like this. Something that looks like this. And this is very, very important. This is potentially useful in the future because you know how we burn fossil fuels, creating carbon dioxide, and we're looking for sustainable fuel alternatives. So solar power is good, wind power is good, stuff like that, like hydroelectric power, nuclear power, but we don't have a way to like really store these, store the energy from sources like that. Like you cannot power your car using solar power, right? You have to either use batteries or you can use an alternative fuel, and that alternative fuel is hydrogen. So hydrogen has been explored as a potential fuel for cars. But we need a way to store this hydrogen because hydrogen, you know, is very dangerous, very explosive gas. So this is one potential way to store hydrogen, since we can split up these hydrogen molecules into forms that are much more easily accessible. This is much easier to store. So maybe in the future you might see this technology emerging. Yeah. And I do want to talk about buffers. So every day you eat acids, acidic foods, and maybe basic foods. So like today I had a salad which had a vinaigrette in it. So vinegar, very acidic. I made a tomato souffle yesterday, so tomatoes are also very acidic. Yeah, so we are constantly consuming acids and bases, and we're also constantly breathing in carbon dioxide. We're constantly breathing in oxygen and expelling carbon dioxide. So you might expect the pH of the body to change very quickly since we're consuming all these acids and we're expelling carbon dioxide and all that stuff. but the human body pH is actually very stable. Your body can only survive a very small change in pH. If you have like a 0.1, 0.2 change in pH, you'll die, right? So how does the body keep the pH constant? The body is a buffer. It's more specifically, it uses the carbonate bicarbonate buffer, if I'm not mistaken. And the idea behind this is we have a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. For example, we have maybe so we have a weak acid and its conjugate base. So let me write down the reaction. So this tells us that H plus times NH3 divided by NH4 plus equals some constant. Now, the concentration of NH3 and the concentration of NH4 are much, much larger than H plus. These concentrations are much larger than H plus. So what this tells us is that we can assume that these two are constant. So then we end up getting this equation. So we can solve for H plus. And then we end up getting this equation called the Henderson-Hasselbalch. pH equals pKa plus log of A minus over HA, where we have the reaction So we have this equation called the Henderson-Hasselbalch equation. And all I want you to notice is that the only thing that impacts pH is the ratio of A minus and HA. It doesn't matter how much there actually is. All that matters is the ratio between them. Furthermore, a small change in A minus or HA will not significantly impact the pH, since we're taking the logarithm of it. And the logarithm ensures that the change is actually going to be quite small. So this is why systems where you have a mixture of A minus and HA, generic acid, generic base, are going to be very stable towards pH changes. So these are called buffers. Okay? And I think that's the last topic I wanted to talk about. Buffers are not super important for you guys. So I think I've printed out some problems. These are all AP chemistry problems. So, and they're all multiple choice. So can we look at these problems and can you see all of them?